I would like first I would like thanks the organized for this nice conference and happy birthday to Professor Burns. He was so I got my PhD from University of Michigan in the 2006, and he was one of my dissertation committee, and he also read my paper, my thesis. So, and then in 2006 and 2005, I visited his office many times, and I asked many questions, and he always very happy to answer all my questions. So also, he wrote a recommendation letter for the when I apply for jobs after graduation. So okay, so let me start my talk. So its title is kind of long. So it's a type of Leftschetz Hyperplane section theorem on Q-Fano threefolds with Picard number 1 and these singularities. So I guess there is not so many people from algebraic geometry here. So let me just explain what the Leftschetz Hyperplane theorem is now. So firstly, let me state the ordinary Leftschetz Hyperplane theorem. So the theorem is called Leftschetz Hyperplane section theorem. So its setting is like this one. So X is projective manifold, and let's say dimension is n, and D is effective ample divisor. Yes, on X. So here, this ample, so hyperplane means actually the same thing. So it's ample means the hyperplane thing. Okay, so then the Leftschetz hyperplane theorem states that this map is this restriction map is isomorphism. So if I is less than or equal to n minus 2 and the primitive I equal to n minus 1. Okay, so what primitive means, the co-corner of this map is torsion free. Okay, so that's the traditional Leftschetz hyperplane theorem. So here, this D can be some singular, but the ambient thing should be always smooth. So. So in the title, so it's about the Leftschetz hyperplane theorem and on the Q-Fano threefold. So let me just define what Fano threefold is. So Fano varieties. So let's say this is X. What is X? Then it's by definition is projective manifold whose anti-canonical section, anti-canonical class is ample. Okay, then so one can show that it is well known that X is simply connected, and then the stereo duality we have these things. So HI, the structure shape, 1, x, H2, x equal to all 0. Okay, then from this exact sequence of shift, so if you look at this, the cohomology from this, the exact sequence of shift, and with this thing, then you have this one. So Picard group X is isomorphic to X. Okay, then let S2 be a smooth hyperplane section of X, then you have this map. So this hyperplane is actually, S is a smooth divisor such that ample, which is ample. So this hyperplane means that one. So then we have this map. So okay, then we have so H1 of OS is 0. So this is another result from the Leftschetz Hyperplane theorem. So it's okay. So with this one, and again, if you apply this exact sequence to this S, then you have this like this one. So Picard group S is embedded H2 of S Z, and this embedding is also primitive. Okay, then we have let's look at the situation. So then we have H2 of X and H2 of S. Okay, and there is the restriction map here, and so we know that this is a primitive embedding by Leftschetz Hyperplane theorem. So now here we are looking at the case I equal to 2 and n equal to 3, right? So we have this case. So the embedding is primitive. Okay, so here is and so we have this map. Okay, so this is competitive. Okay, so this is isomorphism and this is primitive. So we should have this map is primitive. So this is so some people just say this map is primitive. That is a kind of Leftschetz Hyperplane theorem. Okay. So it's so when a student will start to learn algebraic geometry, this is kind of a basic tool to calculate the invariant of varieties. Like you see maybe students start with the complete intersection of the productive space. Then you just use this Leftschetz Hyperplane theorem repeatedly, right? And then you calculate the invariant of the complete intersection with the adjunction formula. Okay, so it's the very basic tool to calculate invariant of algebraic varieties. Okay. So here in this talk, so I would like to generalize this into case that X is a singular variety, but not general singular variety. It's just some singular Fano variety. Okay. So so before define Q-Fano variety, let me define let me introduce the Calabi-Yau manifold, because the Calabi-Yau manifold has an important role in this the proof of this theorem. Okay, so let me define what Calabi-Yau is. So, let's say this is, so what is it? This is compact Kähler manifold. So let's say Y such that the Kähler calculus is trivial and the cohomology of this one this is 0. So that's the definition of Calabi-Yau manifold. Okay. So when I did my PhD, so I basically is interested in constructing Calabi-Yau manifold. So there is many examples of Calabi-Yau manifold known, but if you look at the Calabi-Yau manifold with Picard number 1, there is not so many, and then so there is and then people find that almost all Calabi-Yau is connected by some web, and then in that picture, people think that Calabi-Yau manifold with Picard number 1 is kind of important. They are kind of generate other Calabi-Yau manifold, and also like situation is like the Fano threefold case. So there is only finitely many Fano manifold, and then people in 3 dimensions they classified. And then they started with just Picard number 1 case, and then the other Fano threefold is kind of blowing up or some modification of the Picard number 1 case. So in also like that situations, in Calabi-Yau case, the Calabi-Yau manifold with the Picard number 1 is kind of fundamental thing. Okay. So if the one handy way of constructing Calabi-Yau manifold is taking double cover over Fano manifold. Okay, so let's look at that construction. So let's say now we just look at the 3-dimension thing. So this is Fano threefold. Okay, then so look at this one. Let's look at this complete linear system. Then so we are just looking at the Fano threefold with Picard number 1. In that case, this linear system always contains smooth sections. So, smooth divisor. Okay. And if you choose such a smooth divisor, then you can make a double cover over X. So X. So 2 to 1 double cover. So branch over along S. Okay. So now you can calculate the canonical class of Y. Then you can show that the canonical class is trivial, and you also verify these conditions here. So in this construction, Y is Calabi-Yau. Okay, and then you also show that H11 of Y is 1 if so actually this is equal to rank of PIC Y. Okay, so if you start with the Fano threefold with Picard number 1, then you can get another Calabi-Yau with Picard number 1. Okay, So if you look at the known example of Calabi-Yau manifold with the Picard number 1, this is around half of them. Majority of them is constructed in this way. Okay. Then so let's look at this Y. Then Picard group of this is now this is length is 1, so there is one generator. Let's call it H. Okay. Then this Y has 3 invariants, so H cubed and H times C2 Y, and the other invariant is topological Euler characteristic of Y. Okay, so in Calabi-Yau threefold with Picard number 1, these 2 invariant is quite important. So if you fix these 2 invariant, there is only finite element in Calabi-Yau. So this 2 invariant is almost specify the Calabi-Yau itself. So, so if you construct Calabi-Yau with pure number 1, then this is the next task is to construct calculate these 3 invariant. Okay. So let's look at this double covering over this Fano threefold. Then how can you calculate the invariant of Y? So for double covering things. So you have the X is Fano threefold, so you know all the invariant of this thing. But the question is how can you calculate invariant of this Y? Okay. Well, at first look, it looks simple, just double cover, and you know all the geometry of X. But if you do the calculation, it's not easy. So if you just look at some arbitrary the smooth variety, and if you look at the double cover of it, and there is a branch locus there, then the calculate invariant of this covering is non-trivial task. It highly depends on the branch locus thing. But in this case, the calculation is kind of easy. So let me do the calculation for this case. Okay. So actually the calculation is just done by the Leftschetz Hyperplane theorem. Okay. So in this case, one can show this fact. So here there is a, so if you look at the pullback of this map on this Picard group, Y, one can show that this is isomorphism. So Y. So look at this diagram. So there is Y and double covering X, and this is branch locus here. So as this branch locus, and
can I have a question?
Sure.
So if you have a Picard not equal to 1 bigger than 1,
then actually the Picard number Y is the same with the Picard number X. The same one.
so if there is a smooth member in it.
Well, not always, but if there is smooth member like S, then you can take a double cover. And if there is if this S is not smooth, let's say it has some normal crossing singularity, you can take the double cover. This is usually some singular Calabi-Yau, and sometimes you can resolve the singularity, and then the resolved thing is Calabi-Yau. So okay, so so let's look at this diagram. So S is branch locus, and then look at the pre-image of this S. Let's call it S prime. So here. Okay, so then there is a map. So the point is S here. So S, we took S from this one. So and the minus kx is already ample. So minus 2x is kx is again ample. So that means S is here hyperplane section. So this is hyperplane section. Also, you can show that this is the hyperplane section. Okay. Then now here you can apply the Leftschetz hyperplane theorem here. So you have Picard group of S prime, and this is Picard group of, this is, the arrow is reversed. So you can you look at the pullbacks. X. Here and then, this is actually isomorphism. This is branch locus. This is same image. So, okay. So this is primitive embedding. So only possible map is here is just isomorphism. Okay. So if you look at this case, so you can just have this fact, and with this fact you can calculate this invariant. And then the reason that you have this fact is S is the hyperplane section, and you can apply the Leftschetz hyperplane theorem. Yeah. So that's why you can calculate the invariant so easily. Okay. So now let's look at the case X is non-singular. X is a singular variety. This is some fan of threefold. Okay. So let's give a definition. So a projective variety X is called a Q-Fano variety. If it has only terminal singularity and the anti-canonical class X is ample. Okay, so so it can be some singular variety, and what terminal singularity means. So, well, in this talk I do not consider the general Q-Fano variety. I will just consider Q-Fano variety with some specific singularity. So I think you don't need to understand the terminal singularities. And then negative case is Weil divisor. So, but this is not necessarily Cartier divisor. But in this case, so one can show that you can multiply some natural number to here, then you can make it Cartier divisor, and then you can think about whether this is ample or not. So in that sense, we have the ample things. So, so in this talk, I mean, this is general definition, but in this talk, I consider Q-Fano threefold with some specific singularity. So Q-Fano threefold with the singularity of type 1 and 1 and 1. Okay, so I only consider this this kind of variety, and this singularity is isolated singularity, and you can the singularity is quite easy. So this singularity is locally isomorphic to this one. So if you look at C3 and then look at this action, so you identify x, y, z with minus x, minus y, minus z. Okay, then at the origin you have some isolated singularity. So we call this type of singularity with this symbol. Okay. So I will just consider Q-Fano variety with this type of singularity. So then why should I consider such a singular Q-Fano, not just a smooth one? Well, I found that, so when I was in PhD student, I tried to construct many Calabi-Yau manifold. And then, well, for Calabi-Yau manifold with Picard number 1, the this kind of thing is already done. So I tried to look at other thing, and I found that some singular Fano variety admit smooth Calabi-Yau double covering. So that's why I consider this kind of varieties. Okay. So so let me give some example of this variety. So the simplest one is like if you have some experience with weighted projective variety, then the most simple example is like this one here. 1 and 1, 2. So that is one singularity, and the singularity type is exactly that one. Okay, and so in 3 dimension, smooth Fano variety is all classified, and so but also for this one, so Q-Fano with threefold with this singularity is also classified. Okay, so we have some kind of the classification for these things. Okay, so so let's take a theorem.
Your Calabi-Yau threefold, double cover.
Yes.
It's also branched at those singular points.
Sure, that's right. That's right. So let me explain that thing. Okay. So let X is those Q-Fano. So this is Q-Fano threefold with singularity of type okay, and and choose smooth S in minus 2k. Okay, so here you can look at this completely linear system, and so this kind of thing is already classified. So if you look at the case, if you look at the Q-Fano threefold with Picard number 1, then you can always choose this S. Okay, then you can the theorem is then that is a double covering. So I 2 to 1 to X. This is branched along S and singularity of this one. Okay, and the point is, and Y is smooth. So even though we start with some singular one, this one is smooth Calabi-Yau. So you can show this is Calabi-Yau. And so if you start with the Picard number 1 Q-Fano variety, then this Y is again Picard number 1. Okay. So this is how construct this Y here. Yes, this is smooth one. So here this is 2S. So this is Cartier. So S all miss this singular point. Okay. So if you some variety goes to this singular point, then they cannot be smooth. Okay. No, that is theorem. So I mean, if you look at the case that Picard number 1 case, there always exists. So actually, according to the theorem proved by Takaki, this is very ample. Always very. Well, no. But so even though this Picard number is not 1, if there exists such smooth thing, then you can do the construction. So the fact is you can calculate the length of okay. So there is a many example of X. not like over 20 examples of such thing. Well, that's comparable with the number of smooth Fano variety with number one. So that's many. So well, you can show this fact easily, but the question is how can you calculate other invariant of this y? Okay, so I want to calculate this h cubed and h times second chunkless of this y. So how can you calculate this one here? Okay, so let's look at the diagram before. I mean, in the smooth case, we use the Leftschetz Hyperplane theorem, right? But in that case, we look at the diagram again. So here, so that is x. Now this is a singular Fano, Q-Fano, and that is S here, and y. The preimage of S is like S prime. This is here, and this is the same one, which is because those are the branch locus. And if you look at the proof map on the Picard groups, the diagram looks like this one. So S prime. Y. This is isomorphism now. Oh. Right? But it's not true. There is something wrong with this picture. Well, X is not smooth one. So if you look at the Picard thing, there would be mistake. So we need to look at the class group. Okay. I mean, because here not every Weyl divisor is Cartier. So I just want to look at the group of the Weyl divisors. Okay. Then you have this map. Yeah. So here S is smooth, so you can just look at the Picard group because class group is identical with the Picard group. Okay, so here, so now S is here, S is smooth section, so S is hyperplane section of X, but X is not smooth, so you cannot use the Leftschetz Hyperplane theorem here. Okay, but here Y is smooth, and this is a smooth one, and then you can show that this is the ample divisor here, so this is primitive embedding here. Okay, and this is the same. So we want to know this map. Okay, so I want to show this map is the isomorphism or some kind of. So there is only two possibilities. This is the Picard number one, and the rank is the rank of this lattice is 1, rank of this lattice is 1. So this is double cover. So there is only two possibilities. So generator goes to generator, or generator goes to 2 times of generator. Okay, so there is only the possibilities. So I want to choose which one is the situation. Okay. Okay. So I mean the final result is this is isomorphism, and then this is primitive embedding. So in the goal of this talk is I want to show this map well, okay, so anyway, so situation is like this. So this is not proved yet, so I will show this thing at the end of this talk. Anyway, so let's state the theorem, which I will prove this talk. So theorem is like this. So let me state the main theorem of this talk. So theorem. Okay, so X is as before. I mean the Q-Fano threefold with those specific singularities. Okay, then consider smooth or quasi-smooth Xn in this linear system. Okay, n is some natural numbers. Okay, so what quasi-smooth means? So, okay, so if n is even, then this negative kx is not Cartier, but if you multiply this thing by some even number, this is Cartier. So there could be some divisor which lists all the singularities of x. Then in that case, xn can be smooth. So in that case, n is even. I require xn is smooth. If n is odd, so in that case, this is not Cartier. Okay, then the divisor in here should go through the singularity of x. So in that case, xn cannot be smooth. But at best case, it has the ordinary double point on singularity of this one. So xn is smooth outside singularity of x and has singularities of type 1 and 1 at x. So if n is odd, then it goes through singularity of x, and then the most mild singularity which this xn can have is just this one. This is the ordinary double point. So in this case, I call it quasi-smooth. Okay. So I look at this setting. Okay, then the result is like this. So this map, class group of xn goes to class group of x. This one is primitive. So this is some generalization of the Leftschetz Hyperplane theorem. Okay. And actually, in this case, this is always equal to Picard group of xn, because this is 2-dimension. This singularity, I mean, sometimes xn is smooth, so in smooth case it's always the same, and then xn is sometimes has this kind of singularity, but this is singularity is Gorenstein. So the variety with this singularity is always the Cartier is variety by all the same thing. So like this one. Okay. So how can I show this one? Okay. Well, I will use this one. So the strategy for proof of this is kind of strange, because in the before, in smooth case, we use the Leftschetz Hyperplane theorem to calculate property of invariant of this thing. But in the proof of this one, I will calculate property of this thing. And then with that, I induce this one. Okay? Then how can I calculate property of this y without using the Leftschetz Hyperplane theorem? Well, the method is degeneration. So okay, so I have some time. So proof step. Well, how to prove? show. X is primitive first. So I will show this one, and then with this one, so you can show this thing is immediately. So let me explain that. Firstly, then how we show this one. So okay. So now we are looking at the case X is Picard number 1 and Picard number 1. So classical of this thing is, let's say this is generated by H. And yeah, something's wrong here. This is Y, yeah. Generated by H. Okay, so let's say this is maybe pi star. Then the pi star is, so let's say those are all ample generator. Then the possibility is H is A times some number H. And this is double covering, so only possibility is A is 1 or 2. Okay? Then, so you take the cube of each side, then you have this like this one. So H cubed equal to, this is like 2 times H cubed equal to A cubed H cubed. Okay. Let me just check. Oh, sorry. Ah, that's right. This is right. Okay. So we need. So I want to show that A equal to 1. That means this is primitive. Maybe. Okay. So I want to show. A equal to, I mean, otherwise, that means 2H cubed equal to H cubed. So I want to show, if you want to show this thing, then that means you show this thing is primitive. Okay? But how can you show that this one? It's kind of complicated. Okay, then, so the basic strategy is like this one. So firstly, you make a degeneration with this property. So this is G prime to delta. Delta is open disk. So this is G in C such that C like this one. And this is some fourfold. Okay, so here generic fiber is a, let's call it, is a deformation of this Calabi-Yau Y and central fiber. Z0 is like this one, so V1, V2, E1, En. So here, let me just explain briefly that this V1 and V2s are some blob of original the Fano threefold. So you just blow up the singularity of that thing, then those are V1 and V2 are some smooth one. And this E1 to En's a copy of P3. Okay? So this n is the number of singularity of x. Okay, so now you just the construct semi-stable degeneration of this y. Okay, so you have this central fiber is like this one. Okay, so now what do you do? So after that, so you calculate H2 of this. So now general fiber is the deformation of y. So you calculate this y, this cohomology by H2 of V1, H2 of V2, H2 of E1, EI, let's just call it EIG. So you can calculate the cohomology of this thing by this one. And you can actually show that H2 of Y is G, this is isomorphic to Picard group of Y. And this is generator is H. And you can show that H cubed is, H cubed, so is 2 times H. So here, with this degeneration method, you just show this one here. Okay? So I think I cannot explain this generation more detail, but the basic strategy is like this one. So you have Y, and then you just construct, you just degeneration of Y such that the central fiber is some bunch of P3s, and then V1 and V2s are related with the original X. Okay?
It's just a copy of X?
No. So V1 is the blowing of X at the singularities. And then V2 is the blowing of a V with some curve. So V1 and V2s are all smooth ones, but it's just come from original X.
And EI is an exceptional device.
That's right. So those are exceptional devices, and with the inserted with this one.
Any two components there intersect in a surface?
That's right. So V1 and V2s are intersect with some KT surface, and this one is like intersect with some P2, which is exceptional devices here.
What would happen if you tried to generate the X before you
Then you have like a central fiber is like let's say G prime 0 is X1. No. Let's say X1, X2 prime. So this is some copy of X, and this is the blowing up of X1 along some smooth curve, but the total space is some singularity. Just blow up. So the singularities type is just these ones. 1 and 1 and 1 and 1. You have this. You just blow up all the singularities there. Then we have this central fiber changed like this one. And then, but still it's semi-stable.
So that you don't have two components, V1, V2, because of the two for the branch cover?
Okay. So you can make the degeneration like just X1 and X2, and those are all copy of X. But in that case, the total space has singularity along some curve. So you just blowing up along the curve, and then just blow down another fiber. Then you have the central fiber is this is copy of X, and another is the blowing of C1. So
Where is the branch? Yeah, branch cell fits in.
Oh, that's like this one. So here, okay, that's good question. So X1. So let's say this is X. This is copy of X. Okay, and let me just explain a little bit more here. So X1 equal to X, and X2 is blowing of X1. It's branch locus is like this one. So branch it. C is like this one. S intersect D. So S is the previous S, and D is here. D is some KT surface here in this linear system. So this is the C is some the curve on KT surface with intersected with S. Okay. So potential locus information is embedded to this curve C here.
X2 is a singular.
Yeah, X also is singular. I mean, the singular at the, you know, but you need to, and then you blow up at the singularities, then you have V1 and V2. Okay. All right, so with this one, with the degeneration method, you can calculate that. So now let's look at the situation here. So final proof is like this one. Okay, so here, let's look at this. Picard group of Y, class group of X. You have a map here, and this is Picard group of Xn. So class group of Xn. Actually, let's just call it Picard group, okay? And this is here, and this one. Okay, so this is original Xn, and this Xn prime is the pre-image of Xn here. Okay, so as I said, this is smooth or quasi-smooth. In both cases, you can look at the pre-image of this Xn. This is smooth here. Okay, so all right. So by the ordinary Leftschetz Hyperplane theorem, this is smooth, so we can apply that. So this is primitive embedding. Okay? And then we showed that this is isomorphism. Okay? So this is no, we didn't show that. So let me see. Oh, we showed that this is isomorphism. Okay, with this one. And yeah, we showed that we showed this thing by degeneration method. Then see, this may be this is commutative. So this is primitive. This is isomorphism. Then these two maps should be primitive, right? I mean this map is the composite of these two maps, and the resulted map is primitive. Then both of them should be primitive. Okay, so that means this particularly this is primitive. So that's the Leftschetz Hyperplane theorem. I want to show that. Okay. So so why look at this problem? Well, originally I'm not interested in proving the Leftschetz Hyperplane theorem, but I just want to calculate the invariant of the Calabi-Yau. But in doing that, just I showed that Leftschetz Hyperplane theorem. So in doing that, I found the Calabi-Yau manifold with this one. So Calabi-Yau threefold with Picard number 1. So the mu Calabi-Yau has this invariant. C2 80 times C2x E of x. This is for 1. Okay. This is 844 negative 88. Yeah, that's it.